Picture this. You're standing at the edge of the universe's most terrifying object. You shine the most powerful flashlight ever created straight up into the cosmos. You watch the beam shoot upward, and then it stops. The light doesn't scatter, doesn't fade. It just freezes in space, fighting against something invisible, then slowly falls back down toward you like a ball you've thrown too weakly into the air. This isn't science fiction. This is real physics, happening right now at the edges of black holes scattered throughout our universe. But here's what will absolutely shatter everything you think you know about reality. Light doesn't just struggle against gravity near black holes. Every single photon of light that has ever existed, including the light bouncing off this screen into your eyes right now, is locked in an eternal battle with gravity. And sometimes gravity wins. What I'm about to reveal to you over the next few hours will fundamentally change how you see every beam of sunlight, every star in the night sky, and the very nature of escape itself. Because the question isn't really whether light can escape gravity's grip. The question is, what does it mean that sometimes the fastest thing in the universe, the thing that defines the very speed limit of reality itself, cannot break free? By the end of this journey, you'll understand why Einstein called this the most beautiful thought I ever had, why it made him realize that space itself could be bent and broken, and why the answer to our question means that you, me, and everything we've ever known exists in a universe that's far stranger than you ever imagined. But before we dive into this mind-bending journey, I need something from you. If you're ready to have your understanding of reality completely transformed, smash that like button right now. And hit subscribe, because this is the kind of content that YouTube's algorithm loves to hide. We're building a community of curious minds here, and I want you to be part of it. Also, drop a comment right now telling me, what country are you watching from, and what time is it where you are? I'm genuinely curious to know how far across the globe this question about light and gravity is reaching. Are you watching this during your morning coffee in Brazil? During a late night in Tokyo? During a lunch break in Germany? Let me know. I read every single comment. Now, let's begin with something that seems simple, but will reveal just how deep this rabbit hole goes. Let me ask you something that sounds absurd. Can you throw a ball so hard that it never comes back down? Of course you can't. Gravity always wins, right? But here's the twist. You actually can. You just need to throw it at about 25,000 miles per hour. Do that, and the ball will escape Earth's gravity forever. We call this escape velocity. Now, this concept isn't new. John Michell, a British natural philosopher you've probably never heard of, figured this out way back in 1783. Think of it like this. Imagine you're at the bottom of a deep well, and you're trying to throw a tennis ball out of it. If you throw too gently, the ball rises partway, slows down, stops, and falls back. But throw hard enough, and it clears the edge and keeps going. Escape velocity is just how hard you need to throw. But here's where Mitchell's mind took a leap that was 2 centuries ahead of his time. He asked a question so profound that it would haunt physics for generations. What if an object was so massive, so incredibly dense, that even light couldn't reach escape velocity? Think about that. Mitchell was working with Newton's theory of gravity, which treated light as little particles, like tiny bullets. And he realized, if gravity affects everything with mass, and light has mass, then maybe, just maybe, there could be a star so massive that light itself would be trapped. He called them dark stars. We call them black holes. Now here's what makes this story absolutely wild. Mitchell was right about the conclusion, but wrong about the reasoning. And the way he was wrong tells us something profound about the nature of reality itself. See, Newton's gravity worked like invisible ropes pulling objects together. Massive objects pulled harder. It was mechanical, intuitive. You could visualize it. And in Newton's universe, yes, you could theoretically have a star massive enough that light couldn't escape. but it would just be really, really massive. Nothing too weird about that, right? Wrong, because in 1905, everything changed. A 26-year-old patent clerk named Albert Einstein was sitting in his office in Bern, Switzerland, probably procrastinating on his paperwork, when he realized something that would shatter Newton's entire worldview. Light doesn't have mass. Not even a little bit. Wait, stop, read that again. Light doesn't have mass. Zero. Zilch. Nothing. This should have killed Michell's dark stars completely. If light has no mass, then gravity shouldn't affect it at all, right? Light should just ignore gravity and go wherever it wants. But Einstein didn't stop there. He spent the next decade tormented by a question. If light has no mass, but massive objects still seem to affect light's path, then what the hell is gravity actually doing? And in 1915, Einstein published his answer, general relativity. And it was so bizarre, so counterintuitive, that even he didn't fully believe it at first. Here's the revelation that should blow your mind. Gravity isn't a force at all. Let me say that again, because this is crucial. Gravity is not a force pulling things together. Gravity is the shape of space itself. Think of it like this. Imagine you're an ant walking on a completely flat table. You walk in a straight line, and you keep going straight forever. Easy, right? Now imagine someone pushes a bowling ball into the middle of that table, and it creates a dent, a depression. Now, when you try to walk in a straight line, you find yourself curving around that dent, even though you're still walking perfectly straight from your perspective. The table itself is bent. That's what mass does to space. The sun doesn't pull the Earth toward it. The sun bends space, and the Earth is simply following the straightest possible path through that bent space. It just looks like pulling from the outside. But here's the kicker that brings us back to light. Light always travels in straight lines through space. Always. It's built into the very nature of what light is. So if space itself is bent, then light will follow that bent space, not because gravity is pulling it, but because light doesn't know the difference between bent space and flat space. It's just following the geometry. This means that yes, massive objects affect light's path, not by pulling on it, but by bending the space that light travels through. So can light escape gravity's grip? We're not even asking the right question yet, because gravity isn't gripping anything. Gravity is the shape of the universe itself, and light is just trying to go straight through a curved universe. But now comes the really disturbing part. If space can be bent a little by the sun, a bit more by a dense star, how bent can space become? Is there a limit? Can space be bent so severely that even a straight line curves back on itself? The answer is yes. And when that happens, we get something so extreme that it breaks our very ability to understand what escape even means. Let me tell you about Carl Schwarzschild. It's January 1916. Einstein has just published general relativity 3 months earlier. The equations are brutally complex, so difficult that Einstein himself thought nobody would ever find an exact solution to them. Einstein figured people would only ever be able to approximate answers. But Schwarzschild wasn't just anybody. He was a German physicist and astronomer serving on the Russian front during World War I. And while literally in the trenches, dodging artillery fire, suffering from a painful autoimmune disease that would kill him within the year, he decided to solve Einstein's equations exactly. Think about that for a second. While war raged around him while he was dying, Schwarzschild did the math that Einstein thought was impossible. And what he found was so disturbing that Einstein himself resisted it for years. Schwarzschild discovered that if you compress any amount of mass into a small enough radius, space doesn't just bend. It breaks. It creates what we now call an event horizon, a boundary in space where the curvature becomes so extreme that not even light can escape. Here's what will blow your mind about this. The Schwarzschild radius, as we call it now, depends only on mass. For Earth, if you compressed all its mass into a ball about the size of a marble, you'd create an event horizon. For the Sun, you'd need to compress it to about 3 kilometers across. For you, your personal Schwarzschild radius is about 10 to the minus 25 meters, smaller than a proton by a factor of billions. This means everything has a Schwarzschild radius. You, me, this planet, a coffee cup, everything. It's just that for most objects, that radius is buried deep inside the object itself, so it doesn't matter. But when you compress something enough, when you force all its mass inside its Schwarzschild radius, something extraordinary happens. Space curves so dramatically that every direction points inward. Not metaphorically, literally, every direction. Imagine you're standing on the surface of Earth, and you look up at the sky. Up is away from Earth, right? Obviously. Now imagine you're standing just inside a black hole's event horizon. You look up, away from the center. What you see isn't the outside universe. You see deeper into the black hole. Every direction you can point, forward, backward, left, right, up, down, all of them lead toward the center. The outside universe no longer exists in any direction you can point. This is what it means for space to be so bent that escape becomes geometrically impossible. Now, here's the crucial bit. It's not that light tries to escape and fails. It's that inside the event horizon, the future direction of all paths leads inward. Moving toward the center isn't something you're forced to do. It's the only thing you can do. It's literally the only direction that time flows. Think of it like this. Right now, you can move east or west, north or south, but you can only move forward in time, never backward. Inside an event horizon, you can move around however you want in space, but you can only move inward toward the center, just as surely as you can only move forward through time. It's not a matter of going fast enough or being strong enough. It's a matter of geometry. The path outward simply doesn't exist anymore. So light doesn't escape a black hole for the same reason you can't travel to yesterday. It's not physically possible. The geometry of space-time won't allow it. But here's where it gets truly bizarre. What about light right at the event horizon? Exactly at that boundary. Can it escape? The answer is perhaps the strangest thing in all of physics. Light at the event horizon doesn't go in and doesn't go out. It just orbits forever. There's a sphere of light trapped at the edge of every black hole, circling endlessly at the speed of light, neither escaping nor falling in. Actually, it's more complicated than that. There's a region just outside the event horizon called the photon sphere, where light can orbit the black hole in unstable loops. Unstable meaning if the light is pointed even slightly wrong, it either escapes or falls in. The photon sphere for a non-rotating black hole exists at exactly 1.5 times the Schwarzschild radius. This means that if you were somehow hovering just outside the photon sphere and you looked to the side, you'd see the back of your own head. The light from the back of your head would curve around the black hole and arrive at your eyes from the other direction. But wait, there's more strangeness. If you're far away from a black hole, watching something fall in, you never actually see it cross the event horizon. From your perspective, the object gets closer and closer to the horizon, but the light from it becomes more and more redshifted, more and more delayed. The object appears to slow down, to freeze, to take an infinite amount of time to cross over. From your external perspective, nothing ever enters a black hole. It just gets frozen at the edge forever. But from the perspective of the thing falling in, it crosses the event horizon in a finite, quite brief amount of time. Both perspectives are correct. Both are really happening. This is the relativity in general relativity. So here's the mind-bending summary. Can light escape gravity's grip at a black hole? If it's outside the photon sphere, yes. If it's exactly at the photon sphere, it neither escapes nor falls. It orbits. If it's inside the event horizon, Escape isn't just difficult, it's geometrically impossible, because escape is no longer a direction that exists in spacetime. But before you think this is just exotic physics that only matters at black holes, let me tell you something that will fundamentally change how you see the universe. This isn't just about black holes. This is about everywhere. Because in a sense that we're about to explore, you are inside a kind of event horizon right now. Remember escape velocity? That speed you need to completely escape a gravitational field? We said for Earth, it's about 25,000 miles per hour. For the Sun, it's about 380 miles per second. For a black hole at the event horizon, it's exactly the speed of light. But here's a question nobody asks. What's the escape velocity of the entire universe? Think about this carefully. You're not just on Earth, which has gravity. You're in the solar system, which has gravity. You're in the Milky Way galaxy, which has gravity. You're in a local group of galaxies, which has gravity. You're in a supercluster of galaxies, which has gravity. All of this mass is pulling on you, creating a combined gravitational field. So what if you wanted to escape the gravitational influence of everything? What speed would you need? The answer is going to blow your mind. You'd need to go faster than light, much faster. But wait, you're thinking, nothing can go faster than light. Einstein proved that, right? Exactly. This means that you cannot escape the gravitational influence of the observable universe. Not ever. Not in principle. The universe itself is, in a very real sense, its own event horizon. You are always and forever gravitationally bound to everything that exists. But it gets even weirder than that. In 1929, Edwin Hubble made a discovery that would fundamentally transform our understanding of cosmic escape. He found that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because they were moving through space. It was because space itself was expanding. The universe is getting bigger, and as it does, everything gets carried apart. Now, at first, this seems like it makes escape easier, right? If space is expanding, objects naturally move apart. But here's the twist that brings us back to light. Space is expanding everywhere, all the time. And in the distant universe, it's expanding so fast that light can't keep up. There is a distance, about 46 billion light years away, where space is expanding faster than light can travel through it. We call this the cosmic event horizon. Light from beyond that distance can never, ever reach us. Not because anything is blocking it, but because the space between us and that light is growing faster than the light can cross it. Think of it like this. Imagine you're on a treadmill, running forward at your maximum speed, but the treadmill is set to go slightly faster than you can run. You're running as hard as you can, and yet you're moving backward relative to your starting point. That's what light is doing at the cosmic event horizon. It's traveling toward us at light speed, and yet it's being carried away from us, even faster by the expansion of space. This means there are galaxies we can see now whose light will never reach us in the future. There are events happening right now that no one in our galaxy will ever witness, not because they're hidden behind anything, but because the expanding universe is erasing them from our possible experience. So here's the disturbing answer to our question in a cosmic context. Light can't escape the expansion of the universe. If light is emitted far enough away, it is geometrically trapped, unable to ever reach us, despite traveling at the universe's speed limit. But there's another layer to this that's even more profound. You see, when we ask, can light escape gravity? We're assuming that light is trying to get somewhere. But what if light isn't trying to escape at all? What if light is just doing what light does, traveling through space-time? And it's our perspective that imposes the idea of escape. Let me introduce you to one of the most beautiful ideas in physics, the geodesic. A geodesic is the straightest possible path through curved space. If you've ever looked at a flight path on a map and wondered why planes don't fly in straight lines, it's because they do. They fly on geodesics. The Earth is curved, so the straightest path across its surface looks curved on a flat map. Light always travels on geodesics through spacetime, always, without exception. It doesn't try to escape gravity or fight against it. It just follows the straightest path through whatever geometry space happens to have. So when we ask if light can escape gravity's grip, we're imposing a framework that doesn't match what's actually happening. Light isn't gripped by anything. Light is freely following the geometry of the universe. Sometimes that geometry allows paths that lead away from massive objects. Sometimes that geometry curves those paths back. And sometimes, as in black holes and at the cosmic event horizon, the geometry makes a way cease to be a meaningful direction. Here's what this means for you. Every time you see starlight, you're seeing light that successfully navigated billions of years of curved spacetime to reach your eyes. That light threaded through bent space around countless stars and galaxies, expanded along with the universe itself, and arrived at exactly this moment in exactly this place to enter your eye. The fact that you can see stars at all is proof that, at least in most of the universe, light can escape. But the dark spaces between the stars, the cosmic voids, the centers of black holes, these are the places where light's journey ends, where the geometry says no further. But we're still missing something crucial. We've talked about whether light can escape, but we haven't asked the deeper question. What is light escaping from? What is the nature of this thing we call gravity? And why does the fastest thing in the universe have such a complex relationship with it? Here's something that will fundamentally change how you think about this entire question. Light is not a thing traveling through space. Light is a wave in the electromagnetic field that exists everywhere in space all at once. I know that sounds like word salad, so let me break it down in a way that will make the rest of this conversation make sense. In the early 1800s, scientists were arguing about whether light was a particle or a wave. Thomas Young's double-slit experiment in 1801 seemed to prove it was a wave. Light would create interference patterns just like water waves. But then in 1905, Einstein showed that light also behaves like particles, little packets of energy called photons, when it interacts with matter. So which is it, wave or particle? The answer is both and neither. Light is an excitation in the electromagnetic field. Think of it like this. Imagine a vast ocean covering the entire universe. This ocean exists everywhere, even in the deepest vacuum of space. Now, when you create a ripple in this ocean, we call that ripple a photon. The ripple travels at light speed. The ripple carries energy. But the ripple isn't a separate thing from the ocean. It's a pattern of movement in the ocean itself. That's what light is. A pattern of oscillation in the electromagnetic field that fills all of space. Now here's why this matters for our question about gravity. The electromagnetic field doesn't have mass. The field is just there, everywhere, always. And when that field oscillates, creating light, that oscillation also doesn't have mass. So why does gravity affect light? Because gravity doesn't care about mass. Let me say that again, because it's crucial. Gravity does not care about mass. Gravity affects everything that moves through space-time, period. Mass, energy, light, even pure information. If it exists, gravity affects it. This is where Einstein's most famous equation comes in. E equals mc. Energy equals mass times the speed of light squared. But there's a deeper version of this equation that most people never see. E squared equals mc squared squared plus pc squared. For light, mass is 0, so this reduces to E equals pc, where p is momentum and c is light speed. This tells us something profound. Light has momentum, not because it has mass, but because it has energy. And momentum means that light follows curved paths through spacetime, just like everything else. But here's where it gets truly weird. In quantum mechanics, which is the physics of the very small, we learned that light isn't just a wave in a field. Light is also a quantum fluctuation, a jitter in the fabric of reality itself. The electromagnetic field is never perfectly still. Even in the vacuum of space, the field is constantly fluctuating, creating virtual photons that pop into existence and vanish in timescales so short they can't be measured. These quantum fluctuations are affected by gravity too. In fact, one of the most bizarre predictions of physics is called Hawking radiation, discovered by Stephen Hawking in 1974. Here's what happens. Near the event horizon of a black hole, quantum fluctuations create particle-antiparticle pairs. Normally, these pairs annihilate instantly. But at the event horizon, one particle can fall in while the other escapes. The escaping particle becomes real, stealing a tiny bit of energy from the black hole. Over immense timescales, this causes black holes to evaporate. So here's the mind-bending part. Light can escape a black hole, but only through quantum mechanics, and only by stealing energy from the black hole itself, and only from right at the edge of the event horizon, and only over timescales longer than the current age of the universe for any black hole larger than a mountain. So technically, yes, light can escape gravity's grip even at a black hole. But practically, for any black hole we'd ever encounter, no. Now let me blow your mind with one more concept that ties this all together: gravitational redshift. When light climbs out of a gravitational well, it doesn't slow down. Nothing can make light slow down in vacuum. Instead, it loses energy. The light becomes redder. Its wavelength stretches out. It's climbing uphill through curved spacetime, and that climb costs energy. Think of it like this. Imagine you're throwing a ball upward. As it rises, it slows down because it's losing kinetic energy, converting it to gravitational potential energy. Light can't slow down, so instead it loses energy by changing color. Blue light becomes red. Red becomes infrared. Infrared becomes radio waves. At a black hole's event horizon, the gravitational redshift becomes infinite. Light trying to escape from exactly at the horizon would need infinite energy to climb out. This is another way of understanding why light can't escape. It would need to become infinitely energetic to do so, which is impossible. So can light escape gravity's grip? The answer depends on how deep in the gravitational well it starts. Gravity doesn't grip light like a hand squeezing an object. Gravity shapes the spacetime that light travels through, and depending on how curved that spacetime is, light either has enough energy to climb out, or it doesn't. There's no grip to break. There's only geometry to navigate. But here's what nobody tells you. This question has been answered differently at different times in the history of the universe. And the answer in the future will be different than the answer today, because the universe itself is changing in ways that fundamentally alter what escape even means. In 1998, two teams of astronomers made a discovery so shocking that it won them the Nobel Prize and fundamentally changed our understanding of the cosmos. Saul Perlmutter, Brian Schmidt, and Adam Rees were studying distant supernova, stellar explosions so bright they can outshine entire galaxies. They were using these as standard candles to measure how the universe's expansion was slowing down over time. Because that's what everyone expected. The Big Bang had thrown everything apart, but gravity was pulling it all back together, slowly winning, gradually decelerating the expansion. Eventually, in the far future, the expansion would stop and reverse, and everything would collapse back into a big crunch. Except that's not what they found. The universe's expansion isn't slowing down. It's speeding up, accelerating, getting faster with each passing moment. This should be impossible. Gravity only attracts. It should only slow things down. So what's pushing the universe apart? The answer is dark energy, and it's the biggest mystery in all of physics. We don't know what it is. We don't know how it works. We just know that it's there, making up about 68% of all the energy in the universe, and it's pushing space itself apart, with ever-increasing force. Now, here's what this means for our question about light escaping gravity. The battlefield is changing. Early in the universe's history, gravity was winning. The universe was dense, matter was dominant, and everything was pulling on everything else. Light could travel, but it was swimming through a universe that was trying to collapse back on itself. Today, we're at a transition point. In our local cosmic neighborhood, gravity still dominates. Galaxies cluster together, stars orbit each other, planets orbit stars. But on the largest scales, dark energy is winning. Space is being pushed apart faster than gravity can pull it together. In the far future, dark energy's dominance will be absolute. Galaxies will accelerate away from each other, so fast that light will never be able to cross the growing gulfs between them. The cosmic event horizon will shrink closer and closer to our galaxy. Eventually, in trillions of years, every galaxy except our own will disappear beyond the cosmic horizon. Future civilizations will look up at the sky and see ... nothing. Just our galaxy, alone in an empty void, with no evidence that anything else ever existed. So here's the profound answer to whether light can escape gravity's grip in a cosmological sense. It depends on when you ask. In the early universe, gravity's grip was stronger. Light could travel, but not far before being swept up in the collapse of matter into structures. Today, light can escape locally, but is trapped cosmologically on the largest scales. In the future, light will be even more isolated, able to travel freely within galaxy clusters, but completely unable to ever cross between them. But there's something even more disturbing about this. You see, when we talk about dark energy pushing space apart, we're not talking about some force being applied to galaxies. We're talking about the geometry of spacetime itself having a property, a kind of inherent tension that causes space to expand. This means that in a sense, dark energy is the opposite of gravity. Gravity curves spacetime in a way that brings things together. Dark energy curves spacetime in a way that pushes things apart. And light, traveling on geodesics through this spacetime, is caught in the middle of a cosmic tug-of-war. Here's the truly mind-bending part. We don't know who's going to win in the long run. If dark energy's strength is constant, then yes, the universe will keep expanding forever, accelerating into infinite dilution. But what if dark energy isn't constant? What if it gets stronger over time? There's a hypothesis called the Big Rip, where dark energy becomes so powerful that it eventually tears apart galaxies, then solar systems, then planets, then atoms, then even spacetime itself. In that scenario, light doesn't escape gravity. Nothing escapes. Everything is ripped to shreds by the expansion of space itself. Or what if dark energy gets weaker over time? What if we're living in a temporary phase, and eventually gravity reasserts dominance? Then we'd get the big crunch after all, where everything collapses back together into a singularity. Or, and this is the wildest option, what if dark energy isn't what we think it is at all? What if it's a sign that our entire theory of gravity is wrong on the largest scales? What if Einstein's general relativity breaks down when you apply it to the entire universe, and we need something deeper, something stranger? This is what keeps physicists up at night, because the answer to, can light escape gravity's grip on cosmic scales, depends entirely on the nature of dark energy. And we literally don't know what dark energy is. But let me bring this back down to something you can wrap your head around with an analogy. Think of the universe as a vast ocean. Gravity is like depth, the pressure of water pulling things down. Light is like a bubble trying to rise to the surface. In the deep ocean, the pressure is so intense that bubbles get crushed before they can rise. That's like being inside a black hole. In shallower water, bubbles can rise easily. That's like our local cosmic neighborhood. But now imagine the ocean itself is expanding, the water molecules spreading apart. If the expansion is slow, bubbles can still move around. But if the expansion accelerates, Eventually, the water molecules spread so far apart that the concept of bubbles rising becomes meaningless. That's the future of our universe. So can light escape gravity's grip? In the expanding universe, gravity doesn't grip at all. Gravity shapes and dark energy pushes, and light travels along geodesics through a space-time that's caught between these two fundamental forces. And the final answer won't be known for trillions of years, when the universe itself reveals which force ultimately dominates. But here's what we do know. Light is resilient. It's been traveling through this expanding, evolving universe for 13.8 billion years. It's crossed cosmic voids, navigated around black holes, climbed out of gravitational wells, and traversed the expanding gaps between galaxy clusters. The fact that we can see the cosmic microwave background, light from when the universe was only 380,000 years old, proves that light can escape almost anything given enough time and the right circumstances. Yet we're still missing a crucial piece of this puzzle, because everything we've talked about assumes that space and time and gravity work the way Einstein said they do. But what if they don't? What if at the most extreme edges of reality, at the centers of black holes, at the moment of the Big Bang, at the quantum scale, the rules fundamentally change? Here's something that will keep you up tonight. We don't have a complete theory of gravity. Einstein's general relativity works brilliantly for large-scale phenomena: planets, stars, galaxies, the universe itself. But at the quantum scale, the scale of atoms and particles, general relativity breaks down completely. And at the same time, quantum mechanics, which perfectly describes the behavior of particles and forces, completely ignores gravity. This is the greatest unsolved problem in all of physics. We don't know how to unify gravity with quantum mechanics. We literally don't know how gravity works at the smallest scales. And this matters enormously for our question about light escaping gravity, because the places where that question becomes most extreme, the center of a black hole, the moment of the Big Bang, are precisely the places where quantum gravity should matter. Let me tell you about the Planck scale, named after Max Planck. It's the scale where quantum effects and gravitational effects become equally strong. It's unimaginably small, about 10 to the minus 35 meters, a billion times smaller than a proton. At this scale, spacetime itself becomes quantum. It doesn't behave like a smooth fabric anymore. It becomes grainy, foamy, probabilistic. At the Planck scale, our entire picture of geodesics, of light traveling on curved paths through spacetime, might completely break down. Because spacetime itself might not be a continuous thing. It might be made of discrete quantum units. Spacetime might be pixelated, like a screen, but with pixels so small that we can't detect them with any current technology. If this is true, then inside a black hole, as you approach the singularity at the center, where all the mass is supposedly compressed to an infinitely small point, you don't actually reach infinite density. Instead, at the Planck scale, quantum effects take over. Maybe the singularity isn't a point at all. Maybe it's a quantum foam of spacetime, churning and seething with quantum fluctuations. And if that's true, then maybe light doesn't get crushed out of existence at the center of a black hole. Maybe it gets transformed. Maybe it tunnels through the quantum foam and emerges somewhere else. Someone else. This is the idea behind theories like loop quantum gravity and string theory, competing attempts to unify gravity with quantum mechanics. In loop quantum gravity, space is made of tiny loops of gravitational field, woven together like a fabric. When you compress matter into a black hole, the loops resist being compressed past a certain point. This creates a quantum pressure that could, hypothetically, cause black holes to bounce, to turn inside out at the quantum level. In string theory, particles aren't points, they're tiny vibrating strings. And spacetime isn't fundamental, it emerges from the interactions of these strings. At the center of a black hole, strings might behave in completely unexpected ways, creating bridges to other parts of the universe, or even to other universes entirely. These ideas are highly speculative. We have no direct evidence for any of them, but they point to a profound possibility. At the extremes of gravity, where our question about light escaping becomes most acute, the very nature of reality might be different from what we imagine. Here's a specific example that shows how quantum mechanics changes everything. Hawking radiation, which we mentioned earlier. Stephen Hawking showed in 1974 that black holes aren't actually black. They emit a faint thermal radiation due to quantum effects at the event horizon. Over immense timescales, this radiation causes the black hole to evaporate completely. So here's the question. When a black hole evaporates, what happens to the information that fell into it? Does it come back out in the Hawking radiation? Does it get destroyed? This is the black hole information paradox, and it's been one of the hottest topics in theoretical physics for 50 years. If information is destroyed, it violates quantum mechanics, which says information is always conserved. But if information escapes, that seems to violate general relativity, which says nothing can escape from inside an event horizon. The current best guess, championed by physicist Leonard Susskind and based on ideas from string theory, is that information isn't destroyed and doesn't escape in the normal sense. Instead, it's encoded on the surface of the event horizon, like a hologram. When Hawking radiation is emitted, it carries away information from the surface, not the interior. The three-dimensional interior of the black hole is actually just a holographic projection of the information stored on the two-dimensional surface. If this is true, and this is where your mind should start melting, then everything we've said about light being trapped inside a black hole is wrong. Not wrong in the sense that we miscalculated, but wrong in the sense that the inside of a black hole might not exist in the way we think it does. The interior might be an illusion, a holographic projection of quantum information encoded on the event horizon. And here's the truly disturbing extension of this idea. Some physicists think this holographic principle might apply to the entire universe. The entire three-dimensional cosmos we live in, including you, me, stars, galaxies, everything, might be a holographic projection of information encoded on a two-dimensional surface at the edge of the universe. If that's true, then the question, can light escape gravity's grip, is asking about the behavior of information in a holographic projection. Light isn't a thing traveling through space. Light is information being processed by the cosmic hologram. I know this sounds like science fiction, but this is real physics being worked on by real physicists at places like Princeton and Stanford and Cambridge. And the reason they're pursuing these ideas is because when you try to understand gravity at the quantum level, you're forced to question the very nature of space, time, and reality itself. Now let me bring this back to something concrete. There's an experiment that's been proposed, though we lack the technology to do it, that could test whether spacetime is quantized. If you could measure the position of a mirror with incredible precision, beyond a certain point, you'd encounter quantum fluctuations in the spacetime itself. The mirror wouldn't just be jiggling due to thermal effects or quantum effects of the atoms it's made of. Spacetime itself would be jiggling, and the mirror would be vibrating along with it. If we could detect that, we'd have direct evidence that spacetime is quantized. And that would revolutionize our understanding of how gravity works at the smallest scales. It would tell us that at some fundamental level, geodesics aren't smooth curves. They're jagged, probabilistic paths through quantum foam. And light following those paths isn't smoothly curving through space. It's hopping from quantum to quantum, like a character jumping from pixel to pixel on a video game screen, but so fast and on such a small scale that it looks smooth to us. So can light escape gravity's grip in a quantum universe? We don't know. We literally don't know because we don't have the theory yet that would let us answer that question. We have hints, clues, mathematical frameworks that might be right, but we don't have the full picture. What we do know is this. At the extremes, where gravity becomes strongest and quantum effects become important, our entire framework for understanding light, spacetime, and escape breaks down. The question itself might not make sense in the way we're asking it, because light and gravity and escape might all be emergent phenomena, things that appear at large scales, but dissolve into something stranger and more fundamental when you look closely enough. And yet, despite all this quantum weirdness, despite the fact that our theories break down at the extremes, light still travels. Photons still move through the universe, carrying energy and information, following paths that we can predict with Einstein's equations to stunning precision. The quantum mysteries matter at the Planck scale and at the centers of black holes, but for the vast majority of the universe, the classical picture still works. So we live in a strange middle ground, classical enough that we can see stars, quantum enough that the stars shouldn't exist according to classical physics alone, relativistic enough that black holes can trap light, but quantum enough that black holes eventually evaporate, releasing that light back to the universe in scrambled form. This is the real answer to our question. Light's relationship with gravity is more complex, more nuanced, and more deeply intertwined with the fundamental nature of reality than we ever imagined. And we're still figuring it out. Now I'm going to tell you about something that's going to twist your brain into a pretzel: gravitational waves. These are ripples in spacetime itself, and they're going to force us to rethink everything we've said about gravity. In 1916, the same year Karl Schwarzschild discovered black holes on the Russian front, Einstein predicted that violent cosmic events should create waves in the fabric of spacetime, much like dropping a stone in a pond creates ripples on the water's surface. But these ripples are different. They're not waves traveling through space. They're waves in space itself. For 100 years, this remained just a mathematical prediction. Einstein himself doubted whether gravitational waves were real or just mathematical artifacts. But on September 14, 2015, something extraordinary happened. Two black holes, each about 30 times the mass of the Sun, spiraled into each other 1.3 billion light years away. As they merged, they converted 3 solar masses worth of matter into pure gravitational wave energy in a fraction of a second. That's more power than all the stars in the observable universe combined, released in a burst shorter than a heartbeat. And we detected it. The Laser Interferometer Gravitational Wave Observatory, LIGO, picked up the signal. 2 facilities, one in Louisiana and one in Washington State, each with arms 4 kilometers long, detected spacetime itself, stretching and squeezing by less than 1,000th the diameter of a proton. Let that sink in. We detected the fabric of reality vibrating. We felt the universe ring like a bell from an event that happened over 1 billion years ago. Rainer Weiss, Kip Thorne, and Barry Barish won the Nobel Prize for this discovery. And for good reason. Because gravitational waves change everything about how we understand gravity and light. Here's why. Gravitational waves travel at the speed of light. Exactly the speed of light. Not approximately. Exactly. This tells us something profound about the relationship between gravity and light. They're more similar than we thought. See, in Einstein's theory, both light and gravity are manifestations of space-time geometry. Light is a wave in the electromagnetic field that propagates through space-time. Gravity is a wave in space-time itself, but both propagate at the same cosmic speed limit. This raises a fascinating question. Can gravitational waves escape gravity's grip? Think about this carefully. When 2 black holes merge, they create gravitational waves. Those waves propagate outward at light speed through the curved spacetime around the black holes. But that spacetime is severely curved by the black holes themselves. So the gravitational waves have to travel through bent spacetime created by the very objects that generated them. Can they escape? The answer is yes, but with a twist. Gravitational waves can escape black holes, but only if they're created outside the event horizon. The collision of two black holes happens at the moment they merge, which is right at the combined event horizon. The waves are generated in the final moments before the horizons merge, and they barely escape. In fact, there's a phenomenon called the ringdown, where the newly merged black hole vibrates like a struck bell, emitting gravitational waves as it settles into a stable configuration. These waves carry information about the black hole's mass, spin, and charge. They're literally the sound of space-time ringing. But here's what will blow your mind. Those gravitational waves stretched and squeezed every particle, every atom, every molecule between that merger and Earth for 1.3 billion years. You, personally, were stretched and squeezed by those gravitational waves when they passed through Earth in 2015. You didn't notice because the effect was smaller than an atom, but it happened. Space-time itself was distorted inside your body. Now, here's where it connects back to light. When a gravitational wave passes through space, it changes the distance between objects. This means it changes the time light takes to travel between those objects. LIGO works by bouncing laser beams back and forth along its arms and measuring the time difference. When a gravitational wave passes through, one arm temporarily becomes longer and the other becomes shorter, and the laser light takes different times to travel down each arm. That's how we detect the waves. So gravitational waves affect light's path. But light doesn't affect gravitational waves. This asymmetry is important. It tells us that gravity is more fundamental than electromagnetism. Light is excitations in a field that exists in spacetime. Gravity is excitations in spacetime itself. But there's something even more profound here. When we detected gravitational waves from that black hole merger, we also looked for light from the same event. We didn't see any. Black hole mergers don't produce light because black holes don't have surfaces or matter to heat up. They're pure warped spacetime. But in 2017, LIGO detected gravitational waves from a different kind of event, the merger of two neutron stars. And this time, telescopes all over the world detected light from the same event. Gamma rays, X-rays, visible light, infrared, radio waves. The whole electromagnetic spectrum lit up. This was the birth of multi-messenger astronomy. We detected the same cosmic event through two completely different channels, gravitational waves and light. And here's what's fascinating. The gravitational waves and the light arrived at Earth within 2 seconds of each other after traveling 130 million years. This tells us that gravity and light travel at almost exactly the same speed over cosmic distances. Almost exactly. Not quite the same, there was a 2-second difference. But close enough that it constrains a lot of theories about how gravity works. Some theories of modified gravity predict that gravitational waves should travel at different speeds than light. The fact that they arrive within 2 seconds after 130 million years rules out a huge swath of those theories. It tells us that whatever gravity is, it's intimately connected to the speed of light, to the structure of spacetime itself. So here's the answer to whether gravitational waves can escape gravity. Yes, but they're also gravity. They're not escaping from gravity. They are gravity propagating through itself. It's like asking whether water waves can escape water. The question doesn't quite make sense, because the waves are made of the medium they're traveling through. But this raises an even deeper question. If gravitational waves are ripples in spacetime, and light travels through spacetime, then light must be riding on gravitational waves all the time. Every photon that's ever traveled across the universe has been jostled by countless gravitational waves from countless cosmic events. The path of every beam of light is a complex, wiggly trajectory through spacetime that's been stretched and squeezed by passing gravitational waves billions of times. And yet, somehow, light still arrives. Somehow, despite all this chaos, photons from distant galaxies still manage to travel billions of light years and land exactly on our telescopes. The universe is a turbulent ocean of gravitational waves, And light is a fleet of ships sailing across that ocean, arriving at distant ports despite the constant churning of the cosmic seas. This resilience, this ability of light to navigate through curved, stretching, squeezing, expanding spacetime, and still maintain its identity, still carry information across cosmic distances, is perhaps the most remarkable thing about light. It's not just whether light can escape gravity's grip. It's that light perseveres through a universe that's constantly trying to scramble, redirect, and confuse it, and yet the light endures. We need to talk about what escape actually means, because this question is more philosophically loaded than you might realize. When we ask if light can escape gravity's grip, we're implicitly asking whether information can leave a gravitational system, because light carries information. Every photon encodes data about where it came from, what created it, what it bounced off of. Light is a messenger, a carrier of information across cosmic distances. So the question becomes, can information escape gravity? This brings us back to the black hole information paradox, but now we're going to dig deeper into what it really means and why it's been tearing apart the foundations of physics for decades. In quantum mechanics, information is never destroyed. It can be scrambled, transformed, hidden, but never destroyed. This is called unitarity, and it's one of the most fundamental principles in quantum theory. If you know the complete quantum state of a system at one time, you can in principle calculate its complete state at any other time, forward or backward. Information is conserved. But black holes seem to destroy information. If you throw a book into a black hole, all the information in that book, every word, every letter, every atom's precise position, disappears behind the event horizon. From the outside, all you can measure about the black hole is its mass, spin, and electric charge. Everything else is hidden. John Wheeler famously said, "Black holes have no hair," meaning they have no distinguishing features beyond those three numbers. So where did all that information go? Is it destroyed? That would violate quantum mechanics. Is it somehow encoded in those three numbers? That seems impossible. Three numbers can't store the information from an entire book, much less from all the stars and planets and spaceships that might fall into a black hole over its lifetime. This is where Stephen Hawking's radiation comes back in. When Hawking discovered that black holes evaporate, he initially argued that the information really was destroyed. The radiation coming out was purely thermal, random, carrying no information about what fell in. If true, this would be revolutionary. It would mean quantum mechanics is wrong at a fundamental level. But most physicists couldn't accept this. It felt wrong. Information has to be conserved. So they started looking for ways that information could escape from black holes through the Hawking radiation. In the 1990s, Leonard Susskind and Gerard 't Hooft proposed the holographic principle we mentioned earlier. The idea is that all the information about what falls into a black hole is encoded on its event horizon, like a hologram. The surface area of the event horizon, measured in Planck units, tells you the maximum amount of information the black hole can store. When Hawking radiation is emitted, it's actually carrying away information from the horizon, not from the interior. But there was a problem. If you calculated carefully, it looked like the information would take more than half the black hole's lifetime to start coming back out. For the first half of the evaporation process, the radiation appeared to be purely thermal, carrying no information. Then suddenly, in the second half, all the information had to come rushing out. This was called the firewall paradox, because it seemed to imply there would be a wall of high-energy radiation right at the event horizon that would incinerate anything trying to cross. In 2019, a group of physicists including Doane Page and Jeff Pennington made a breakthrough. Using advanced mathematical techniques from string theory, they showed that information actually starts coming out immediately in the Hawking radiation. It's just encoded in subtle quantum correlations that are incredibly difficult to detect. The information doesn't come out in a rush. It seeps out gradually, encoded in the quantum entanglement between the particles that escape. This means that yes, in a sense, light can escape from a black hole. Not the light that falls in, that's gone. But the quantum information carried by that light can eventually escape through Hawking radiation, scrambled and encoded in ways that we're only beginning to understand. But here's what keeps me up at night. This only works if we assume quantum mechanics is exactly right, and general relativity is just an approximation that breaks down in small scales. If both theories are exactly right, the paradox is unsolvable. Information cannot both be conserved, quantum mechanics, and hidden behind an event horizon forever, general relativity. Something has to give. Most physicists bet on general relativity giving way because quantum mechanics has never been wrong. Every prediction of quantum mechanics has been tested and confirmed to absurd precision. But general relativity has also never been wrong when we can test it. The universe seems to be telling us that both theories are right, even though they contradict each other at the extremes. This brings us to a profound realization about escape. Maybe escape isn't about physically leaving a region of space. Maybe escape is about information, about influence, about causal connection. If information from inside a black hole can eventually influence the outside universe through the correlations in Hawking radiation, then in some sense, that information has escaped, even though no single particle traveled directly from inside to outside. Think of it like this. Imagine you burn a book. The book is destroyed, but the information isn't truly gone. It's encoded in the exact positions and momenta of every smoke particle, every photon of light emitted by the fire, every scattered atom. In principle, with perfect knowledge and infinite computing power, you could reconstruct the book from the ashes and smoke. The information escaped the book by being scrambled into the environment. Black holes might work the same way. Information doesn't escape as coherent light or matter. It escapes as quantum entanglement, as correlations between particles that are individually random but collectively encode everything that fell in. So can light escape gravity's grip? Not as light, but as information, scrambled through quantum processes we're still struggling to understand? Yes, eventually, given enough time. Through mechanisms so subtle that we've only just begun to detect them mathematically. But there's one more layer to this. Some physicists, including Juan Maldacena, who discovered a deep connection between string theory and quantum field theory, have suggested that the interior of a black hole might be connected to distant parts of the universe through quantum entanglement, that the geometry of spacetime might be emergent from quantum entanglement patterns, that here and there might be illusions created by how information is connected, not by physical distance. If this is true, then when light falls into a black hole, it doesn't really go somewhere else. It becomes entangled with the quantum state of the black hole, which is itself entangled with the rest of the universe in ways we don't understand. The light doesn't escape. It dissolves into the quantum substrate of reality itself. This is the cutting edge of theoretical physics right now, and nobody knows if any of it is right. But what we do know is that the question, can light escape gravity's grip, has forced us to confront the deepest mysteries about information, quantum mechanics, gravity, and the nature of reality itself. And here's the beautiful, frustrating, exhilarating truth. We might not know the complete answer for decades, maybe centuries. This is a problem that's been unsolved for 50 years, and it touches on questions that are so fundamental that answering them might require a complete revolution in how we think about physics. Now I'm going to tell you about one of the most mind-bending possibilities in all of physics: wormholes. Because if wormholes exist, then light can escape gravity in a way that's far stranger than anything we've discussed so far. A wormhole is a tunnel through spacetime, connecting two distant points through a shortcut. Instead of traveling billions of light years across the universe, you could travel a few meters through a wormhole and emerge on the other side of the galaxy, or the universe, or even in a different universe entirely. Einstein and his colleague Nathan Rosen discovered wormholes mathematically in 1935. They were studying the geometry of black holes and realized that the equations allowed for solutions where a black hole's event horizon connects to a white hole, a theoretical object that's the time reverse of a black hole, something that nothing can enter, but everything can leave. A bridge between them is a wormhole, an Einstein-Rosen bridge, as it's technically called. Here's the catch: the bridge collapses. In the time it would take light to travel through the wormhole, the throat pinches off, disconnecting the two ends. Anything trying to traverse the wormhole would be crushed as space-time itself pinched closed. But in the 1980s, Kip Thorne and his colleagues at Caltech were contacted by Carl Sagan, who was writing a science fiction novel called Contact. Sagan wanted a scientifically plausible way to send his characters across the galaxy. Could wormholes work? Thorne did the calculations and found something remarkable. Yes, you could keep a wormhole open, but only if you threaded it with exotic matter that has negative energy density. This is matter that pushes instead of pulls. It creates anti-gravity instead of gravity. Does such matter exist? Incredibly, yes. Kind of. The Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948, shows that quantum vacuum fluctuations can create regions of negative energy between closely spaced metal plates. It's been measured in laboratories. It's real. So traversable wormholes might be possible. Not with our current technology. We'd need to manipulate quantum vacuum energy on cosmic scales, which is so far beyond our capabilities, it might as well be magic. But maybe, someday, an advanced civilization could create and stabilize a wormhole. Now here's where this gets relevant to our question about light escaping gravity. If you fell into a black hole, but that black hole was connected to a wormhole, you wouldn't hit a singularity. You'd travel through the wormhole and emerge somewhere else. You'd escape, not by climbing out of the gravitational well, but by taking a shortcut through space-time itself. Light could do the same thing. A photon entering a wormhole entrance would exit from the other mouth almost instantly, having crossed cosmic distances through a path that bypasses normal space-time entirely. So in a universe with wormholes, light can escape gravity's grip by not playing the game at all, by tunneling through space-time rather than traveling across it. But there's a darker possibility too. Some solutions to Einstein's equations allow for closed time-like curves paths through space-time that loop back on themselves, allowing travel to your own past. Wormholes might create these. You could send light through a wormhole and have it arrive before it left. This creates all sorts of paradoxes. What if you sent a signal through the wormhole telling your past self not to send the signal? What if light trapped in a closed time-like curve could never escape because it's eternally looping through the same moment? Most physicists think nature must have some protection mechanism that prevents these paradoxes, something that makes closed time-like curves impossible even if the math allows them. But we don't know what that mechanism is. Stephen Hawking proposed something he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel, that quantum effects would destroy any wormhole that tried to create a closed time-like curve. But he couldn't prove it. It remains a conjecture. So here's the bizarre state of affairs. The mathematics of general relativity allows for wormholes, time travel, and shortcuts through space-time. Light could theoretically escape gravity by taking these shortcuts, by exploiting exotic geometries that bypass normal rules. But we don't know if these solutions correspond to physical reality. We don't know if nature allows them. What we do know is that every time we've discovered a weird prediction of general relativity and thought surely that can't be real, nature has surprised us. Black holes seemed absurd until we found them. Gravitational waves seemed absurdly weak until we detected them. The expansion of the universe seemed impossible until we measured it. So maybe wormholes are real. Maybe light can escape gravity by traveling through tunnels in spacetime. Or maybe there's some deeper principle we haven't discovered yet that rules them out. But here's what fascinates me about this possibility. It suggests that escape might not be about overcoming gravity at all. It might be about finding paths through spacetime that weren't obvious. About exploiting the geometry of reality in clever ways. This connects to something profound about quantum mechanics. In quantum theory, particles don't have single paths. They take all possible paths simultaneously, and the paths interfere with each other quantum mechanically. A photon traveling from point A to point B doesn't just take the straight path. It takes every possible path through spacetime, including paths that go backward in time, paths that loop around, paths that go arbitrarily far away before coming back. Most of these paths cancel each other out through quantum interference, and what we see is the photon taking what looks like a straight line. But fundamentally, the photon is exploring all of spacetime, tunneling through every possible geometry, testing every possible escape route. So in quantum mechanics, light is already taking wormhole-like shortcuts. Not macroscopic wormholes, but quantum fluctuations in spacetime geometry that briefly open up alternative paths. On average, these paths add up to the classical geodesic we expect. But at the quantum level, light is doing something far stranger, far more exploratory. This suggests that the question, can light escape gravity, is asking about the sum of all possible paths through spacetime, weighted by their quantum amplitudes. Some paths escape easily, some paths loop back, some paths tunnel through quantum foam. And the light we see is the superposition of all these possibilities. In this view, light doesn't just escape or fail to escape. Light exists in a quantum superposition of escaping and not escaping. And only when we measure it does it collapse into one outcome or the other. The event horizon of a black hole isn't a hard boundary. It's a probabilistic threshold where the quantum amplitude for escape paths becomes exponentially suppressed. This is the frontier where quantum mechanics and gravity meet, where our understanding is shakiest, and where the most profound mysteries remain. And it's where the answer to our question becomes not a simple yes or no, but a quantum maybe, a superposition of possibilities that only resolves when information reaches an observer. Let me tell you about the saddest fact in cosmology. There is light traveling through the universe right now, light that has been traveling toward Earth for billions of years, light that will never reach us, not because something is blocking it, not because it's inside a black hole, but because the universe is expanding too fast. We talked earlier about the cosmic event horizon, that boundary beyond which space is expanding faster than light can travel through it. But I want you to really understand what this means emotionally, conceptually, because this is where the question of light escaping gravity becomes cosmically tragic. Imagine a galaxy 20 billion light years away. At the moment of the Big Bang, that galaxy's matter was very close to ours. The universe was tiny, dense, hot. Then space expanded, carrying that galaxy's matter and our matter apart. For billions of years, light from that galaxy was able to reach us. The space between us was expanding, yes, but slowly enough that light could make progress. But then dark energy kicked in. The expansion accelerated. And at some point, relatively recently in cosmic history, light from that galaxy stopped making progress toward us. It's still traveling at light speed through space, but space is expanding so fast that the galaxy is receding from us faster than its light can approach. That light is running on a treadmill set too fast. It's trying as hard as the universe allows anything to try, and it's losing ground. And here's the heartbreaking part. In the far future, most of the galaxies we can see now will cross this horizon. They'll accelerate away from us until their light can no longer reach us. And then they'll vanish. Not because they were destroyed, not because they went out, but because the space between us and them grew too fast for information to cross. Future civilizations in our galaxy will look up at the sky and see almost nothing. Our own local group of galaxies, held together by mutual gravity, and beyond that, darkness. Empty, expanding void. They'll have no evidence that the Big Bang happened. The cosmic microwave background, that faint glow from the early universe that we can still detect today, will be redshifted and diluted into undetectability. They'll have no evidence that dark energy exists. From their perspective, the universe will appear static, unchanging, just our local cluster of galaxies surrounded by nothing. All the cosmology we've learned over the past century, that the universe is expanding, that it started with a Big Bang, that it's filled with billions of galaxies, will be unknowable to them, unless we leave behind records, messages, archives. Future scientists will dig up our data and read about a universe they can no longer see. They'll have to trust that we weren't lying or mistaken. So can light escape gravity in this scenario? No. Light from distant galaxies is trapped by the expanding space between us and them. Not trapped in a place, but trapped in time. The information in that light will never propagate to us. It's causally disconnected, forever. But there's something even more subtle going on here. You see, the cosmic event horizon isn't a fixed distance. It's constantly changing as the universe evolves. Right now, the cosmic horizon is about 16 billion light years away. In the past, it was closer. In the future, it will be farther. This means there's a shell of galaxies that are currently just inside our cosmic horizon, but they're moving outward. Eventually, they'll cross it and disappear. There's a last photon from each of those galaxies that will reach us, and after that, nothing. Ever. We are living in a special time, cosmically speaking. We can see evidence of the Big Bang. We can detect the cosmic microwave background. We can observe distant galaxies and measure the expansion rate. In the far past, the universe was too young and too opaque for these observations. In the far future, the universe will be too expanded and too empty. We're living in the cosmic epoch when cosmology is possible. And that's not a coincidence. We can only exist during an epoch when stars are forming, planets are stable, and life has time to evolve. This is a form of anthropic principle. We observe a cosmos where cosmology is possible because we couldn't exist in a cosmos where it wasn't. But here's what this means for our question about light escaping gravity. The answer depends on when you ask. In the early universe, gravity dominated and light couldn't travel far before being absorbed or scattered. Now, light can travel vast distances, but dark energy is starting to win. In the future, light will be able to travel freely within our local gravitational structure, but nowhere beyond. The universe is transitioning from a gravity-dominated regime to a dark energy-dominated regime, and light is caught in the middle of this cosmic phase transition. There's a poetic way to think about this. Light is the universe's way of communicating with itself. Photons carry information from one place to another, allowing distant parts of the cosmos to influence each other, to stay in causal contact. But as the universe expands, that communication network is being broken. The cosmos is fragmenting into causally disconnected islands, each one unable to send or receive signals from the others. In the ultimate future, each island will be completely isolated. Light will be able to travel within each island, but never between them. Gravity's grip won't be what traps the light. The expansion of space itself will be the prison. But here's a thought that gives me chills. Maybe this has already happened. Maybe we're already inside a causally isolated bubble, and there are regions of the universe that we can never see, never know about, never influence. Maybe the observable universe is just one island in an infinite ocean of islands, each one isolated by the accelerating expansion. And if that's true, then the question, can light escape gravity, becomes, can light escape its own cosmic neighborhood? And the answer is no. Not now. Not ever. Light, the fastest thing in the universe, The thing that defines the speed limit of causality itself is ultimately trapped by the geometry of expanding spacetime. This isn't a failure of light. It's a fundamental property of the universe we inhabit. And it means that there are truths about the cosmos that we will never know, questions we can never answer, because the information to answer them is forever out of reach, sealed behind a horizon we can never cross. All right, we've spent over 2 hours diving deep into theory, mathematics, and cosmic speculation. But let's bring this back down to Earth, literally. How do we actually test whether light can escape gravity? What experiments have we done, and what have we learned? First, let's talk about gravitational lensing. This is one of the most direct confirmations that gravity affects light. In 1919, just 4 years after Einstein published general relativity, astronomers led by Arthur Eddington mounted expeditions to observe a total solar eclipse. The idea was brilliant. During the eclipse, you can see stars near the sun in the sky. If gravity bends light, those stars should appear shifted from their normal positions. Einstein predicted the shift would be twice what Newton's theory would predict. Newton said light has mass and gravity pulls it. Einstein said gravity bends space and light follows the curves. The predictions were different enough to distinguish. Eddington's team photographed stars near the sun during the eclipse and compared them to photographs of the same stars when the sun wasn't there. The stars were shifted by exactly the amount Einstein predicted. This made Einstein instantly famous. The headline in the New York Times read, "Lights all askew in the heavens." Einstein had overthrown Newton's 200-year-old theory of gravity. And he did it by showing that light doesn't just travel in straight lines. It follows the curved geometry of spacetime. Since then, we've observed gravitational lensing countless times. We've seen light from distant galaxies bent around massive galaxy clusters, creating beautiful Einstein rings and multiple images of the same galaxy. We've used gravitational lensing to map dark matter, to measure the expansion rate of the universe, to find distant planets. Every single observation confirms that gravity affects light exactly as Einstein predicted. Light can't escape the influence of gravity. It follows geodesics through curved spacetime. But here's a more extreme test. We've observed light trying to escape from near black holes. There are stars orbiting very close to the supermassive black hole at the center of our galaxy, Sagittarius A*. One of them, called S2, has an orbit that takes it within 17 light hours of the event horizon. When S2 is at the closest point in its orbit, we can measure how gravity affects the light coming from it. The light is gravitationally redshifted, exactly as predicted. The star's light loses energy climbing out of the black hole's gravitational well. The light doesn't slow down, it's Renner. This is direct confirmation that light struggles against gravity. Not struggles in the sense of exerting effort, but struggles in the sense that it pays an energy cost to escape. Now, let's talk about an even more extreme test, the Event Horizon Telescope. In 2019, an international collaboration of radio telescopes spanning the entire Earth captured the first image of a black hole's event horizon. Actually, they imaged M87*, a supermassive black hole 55 million light-years away. What they saw was a dark circle surrounded by a bright ring of light. That dark circle is the black hole's shadow, the region where light can't escape. The bright ring is light that's orbiting just outside the photon sphere before either escaping or falling in. This image is direct evidence that there exist regions of spacetime where light cannot escape. The dark circle isn't dark because there's nothing there emitting light. It's dark because any light emitted there is trapped and can't reach us. Katie Bouman, one of the scientists who developed the imaging algorithms, described it beautifully. We've been studying black holes for so long that sometimes it's easy to forget that none of us have ever seen one. Now we have. And what we see confirms that yes, there are regions where light cannot escape gravity's grip, not because we can't see well enough, but because the geometry of spacetime makes escape impossible. But let me tell you about an experiment that's even more direct, one that's been ongoing for decades: the Gravity Probe B mission. Launched in 2004, this satellite carried 4 of the most perfect spheres ever made gyroscopes, so precisely spherical that if they were scaled up to the size of Earth, the tallest mountain would be only 8 feet high. These gyroscopes were used to test 2 predictions of general relativity: the geodetic effect and frame dragging. The geodetic effect is how space curves around Earth. Frame dragging is how rotating mass literally drags spacetime around with it, like honey swirling around a spoon. Both effects were confirmed to incredible precision. This tells us that gravity isn't just bending the paths that light takes through space. It's bending space itself, and rotating mass twists space like a vortex. Light traveling through this twisted spacetime has to follow those twists. Now let's talk about something you can actually test yourself right now with equipment you probably have access to: GPS satellites. Your phone's GPS works because satellites orbit Earth, broadcasting precisely timed signals. Your phone receives signals from multiple satellites and calculates your position based on the time delays. But here's the thing: those satellites are moving fast, and they're farther from Earth's gravity, well, than you are. Special relativity says moving clocks tick slower. General relativity says clocks in stronger gravity tick slower. Both effects influence GPS satellites. If we didn't account for general relativity, GPS would accumulate errors of about 11 kilometers per day. The system wouldn't work. So every time you use GPS, you're confirming that gravity affects time. And since light travels at a fixed speed, that means gravity affects how far light can travel in a given time. You're testing general relativity with your phone. But let me tell you about the most extreme test that's coming in the near future. The Event Horizon Telescope is planning to image the black hole at the center of our own galaxy, Sagittarius A*. This black hole is much closer than M87*, only 26,000 light-years away. But it's also much smaller and changes much faster, which makes it harder to image. When we get that image, we'll be able to test general relativity in even more extreme conditions. We'll measure the exact size and shape of the event horizon. We'll see how matter spirals in. We'll watch light being bent and redshifted and trapped in real time. And here's what's wild: there are proposals to go even further. The Black Hole Explorer mission, if funded, would use radio telescopes in space to create an even larger virtual telescope, one that could image the photon sphere around black holes in incredible detail. We could literally watch light orbiting black holes, trapped neither inside nor outside, frozen at the edge of escape. There's also the Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave detector planned for the 2030s. Unlike LIGO, which detects high-frequency gravitational waves from stellar mass black hole mergers, LISA will detect low-frequency waves from supermassive black hole mergers. We'll be able to observe gravity itself propagating across the universe, watch space-time ripple, see how those ripples affect everything they pass through, including light. But here's an experiment that really gets at the heart of our question: attempts to detect Hawking radiation. If black holes really do emit quantum radiation and eventually evaporate, we should be able to detect it. The problem is that for any black hole we've actually found, the Hawking radiation is so faint that it's completely swamped by other sources of radiation. The cosmic microwave background is warmer than the Hawking radiation from even the smallest stellar black holes. But physicists have created analog black holes in laboratories. In 2016, Jeff Steinhauer at the Technion in Israel created an acoustic black hole using supercooled atoms. Sound waves in this system behave like light near a black hole, and he detected the acoustic equivalent of Hawking radiation quantum fluctuations that create sound, waves that escape from the analog event horizon. This isn't the same as detecting real Hawking radiation from a real black hole, But it's confirmation that the underlying quantum mechanics works the way Hawking predicted. It suggests that yes, even from black holes, information can escape through quantum processes, just incredibly slowly. Now let me tell you about an experiment that hasn't been done yet, but could revolutionize our understanding: detecting quantum gravity effects. Remember how we talked about spacetime being quantized at the Planck scale? If that's true, we might be able to detect it. One proposal is to look at light from gamma-ray bursts, the most energetic explosions in the universe. These bursts emit light across a huge range of energies. If spacetime is quantized, higher energy photons might travel slightly slower than lower energy ones because they interact with the granularity of spacetime more strongly. The effect would be tiny a delay of milliseconds after traveling billions of light years. But we can measure milliseconds. We have telescopes sensitive enough. And if we detected this, it would be direct evidence that spacetime has a quantum structure, that the smooth geodesics we've been talking about are actually jagged quantum paths at the smallest scales. This would fundamentally change our answer to whether light can escape gravity, because it would mean that light and gravity and spacetime are all emergent phenomena arising from something deeper, something quantum. So here's what all these experiments tell us. Light's interaction with gravity is real, measurable, and exactly matches Einstein's predictions across every scale we can test. From GPS satellites to black hole shadows to gravitational waves, every experiment confirms that light follows the geometry of curved spacetime. Light can escape from most gravitational systems. We see starlight, after all. But light cannot escape from beyond event horizons, and light struggles to climb out of deep gravitational wells, paying an energy cost that redshifts it. And we know this not through pure theory, but through actual measurements, actual observations, actual experiments that you can look up right now. This isn't speculation. This is tested reality. But all of these experiments have been done in the classical regime, where quantum effects average out. The real test will come when we can probe the quantum nature of gravity directly. And that's where the next revolution in physics will happen. Okay, we're about to go deep, really deep, because the question of whether light can escape gravity isn't just about physics. It's about whether anything can truly escape, whether freedom is possible in a deterministic universe, whether the future is fixed or open. Think about it. Light is the fastest thing in the universe. It's the cosmic speed limit. If light can be trapped, if light cannot escape from certain configurations of spacetime, then what hope does anything slower have? What hope do you have? Let's start with a thought experiment. Imagine you're in a rocket ship approaching a black hole. You have your engines on full thrust, pointing away from the black hole. At some distance from the event horizon, your thrust exactly balances the gravitational pull. You're hovering, neither falling in nor escaping. This distance is called the static limit. Now you fire your engines harder. You accelerate upward, escaping. You're free. But now imagine you drift closer to the event horizon, below the static limit. You fire your engines on full thrust. You're accelerating at maximum capability, but you're still falling inward. The geometry of spacetime is so curved that even your maximum acceleration isn't enough to escape. Your future is determined. You will cross the event horizon. There's nothing you can do about it. This is what we mean when we say light can't escape from inside the event horizon. It's not that there's a barrier. It's that the future direction of all possible paths leads inward. The future is geometrically constrained. Now, here's the disturbing question. Are we any different? In classical physics, if you knew the position and momentum of every particle in the universe with perfect precision, you could calculate the entire future. The universe would be deterministic, a clockwork mechanism that started with the Big Bang and will end wherever the equations say it ends. Everything that happens, including your thoughts, your choices, your feeling of making decisions, would all be predetermined by the initial conditions. In this view, Free will is an illusion. You feel like you're making choices, but you're really just following your geodesic through spacetime, determined by the configuration of your brain, which was determined by your genes and experiences, which were determined by physics and chemistry, all the way back to the Big Bang. Just like light can't escape its geodesic, you can't escape yours. But then quantum mechanics came along and said, no, the universe isn't deterministic. At the quantum level, things are fundamentally probabilistic. You can't predict with certainty what will happen. The best you can do is calculate probabilities. So does quantum mechanics save free will? Does it mean that the future is genuinely open, that escape from determinism is possible? Here's where it gets tricky. Quantum mechanics is probabilistic, but it's still governed by equations. The Schrödinger equation tells you exactly how quantum states evolve. If you know the quantum state now, you can calculate the probability distribution for the future. The specific outcome is random, but the range of possibilities and their probabilities are determined. So quantum mechanics trades determinism for randomness, but randomness isn't the same as free will. If your decisions are determined by quantum randomness in your brain, that doesn't make you free. It makes you a random number generator. Some philosophers and physicists have argued that quantum mechanics might provide a mechanism for free will, that consciousness might be able to influence which quantum outcome occurs, to collapse the wave function in a directed way rather than randomly. But there's no evidence for this. It's speculation piled on speculation. Roger Penrose, the physicist who proved many of the fundamental theorems about black holes, has proposed that consciousness involves quantum gravity effects in structures called microtubules inside neurons. He argues that these quantum effects might give rise to genuine non-computational aspects of consciousness that could ground free will. But most neuroscientists are skeptical. So here's where we stand. If the universe is deterministic, then just as light cannot escape the geodesics determined by spacetime geometry, you cannot escape the path determined by the initial conditions of the universe. If the universe is quantum mechanical, then just as light takes all possible paths through spacetime, and the outcome is probabilistic, your decisions might emerge from quantum randomness. Either way, it's hard to find room for the kind of free will that feels meaningful. But wait, there's another perspective that changes everything. What if free will isn't about escaping determinism? What if free will is about being the kind of system that's complex enough to model itself, to reflect on its own processes, to incorporate those reflections into future decisions? Think about it. A rock falling has no free will because it can't model its own trajectory, can't consider alternatives, can't adjust based on self-reflection. But you can. You're reading this right now, thinking about whether you have free will, and that very thought is influencing your future thoughts and actions. In this view, free will isn't about being uncaused or random. It's about being a causally complex system whose behavior is influenced by its own self-models. You can't escape causation any more than light can escape space-time geometry. But you're the kind of causal process that includes self-awareness and self-modification. Light has no choice about following geodesics, but it also has no awareness that geodesics exist. You have no choice about being a physical system following the laws of physics, but you are aware of it. And that awareness itself is part of the physical process that is you. So can you escape gravity's grip in the metaphorical sense? Can you escape determinism, fate, causation? No, but also yes. You can't step outside the causal structure of the universe any more than light can step outside spacetime. But you are part of that causal structure. Your self-awareness, your deliberations, your decisions are all causes that have effects. You're not escaping the causal chain. You're participating in it in a uniquely complex and self-reflective way. This is what it means to be free in a determined universe. Not to be uncaused, but to be self-caused. To be the kind of system whose internal complexity and self-modeling creates genuine degrees of freedom, even within deterministic or probabilistic framework. Light follows geodesics through spacetime. You follow your path through the space of possible experiences and decisions. Neither of you can escape the geometry of the space you're traveling through, but light has no awareness of its path. You do, and that makes all the difference. Here's the truly mind-bending part. By asking whether light can escape gravity, you're exercising the very kind of freedom that makes you different from light. Light can't wonder about its own nature. Light can't ask questions. Light can't seek understanding. You can. You are. Right now. So the answer to whether you can escape, whether freedom is possible, is found in the very act of asking the question. Not because the question lets you escape causation, but because being the kind of thing that asks questions is what freedom looks like from the inside. And just as light, despite being trapped by gravity in certain configurations, manages to travel 13.8 billion years across the universe to reach us, you, despite being constrained by physics and causality, manage to create meaning, understanding, and purpose within those constraints. That's not escape from determinism. That's something better. It's finding freedom within structure, meaning within mechanism, choice within causation. We've spent nearly 2.5 hours journeying through the cosmos, from event horizons to quantum foam, from gravitational waves to the end of time. But now I want to bring this all the way back down to you, sitting wherever you are, reading or listening to these words. Because here's what nobody tells you about physics. It's not just about the universe out there. It's about how you relate to reality itself. Every time you look up at the night sky and see starlight, you're receiving photons that have traveled for years, centuries, millennia. That light escaped from the surface of distant stars, climbed out of their gravitational wells, traversed the curved spacetime of the galaxy, navigated through clouds of gas and dust, and arrived at your eye at precisely this moment. Think about that. The light from Betelgeuse C, that bright red star in Orion's shoulder, left that star about 650 years ago. When that photon began its journey, the year was around 1375. The Renaissance hadn't started yet. The Americas were unknown to Europe. That photon has been traveling through space, following its geodesic, for longer than your country has existed, longer than your language has existed in its current form. And it ends its journey in your eye. You are the destination of light that has been traveling for centuries. But it's more profound than that. The atoms in your body were forged in the cores of stars that exploded billions of years ago. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was created by nuclear fusion inside stars that experienced such extreme gravity that they collapsed and exploded. You are literally made of star stuff that escaped gravity's grip through the most violent events in the cosmos, supernova. The atoms that make up your body escaped from stellar cores through explosions so powerful they briefly outshine entire galaxies. So when we ask, can light escape gravity's grip? We're not just asking about photons. We're asking about the very atoms that make you possible. And the answer is yes sometimes. Through extraordinary events, matter and energy can escape even the most extreme gravitational wells. You exist because escape is possible. But here's what gets me. You are also a temporary configuration of matter and energy that is constantly fighting against entropy, against the universe's tendency toward disorder and equilibrium. Every moment, your body is performing millions of molecular processes to maintain order, to stay alive, to keep thinking. You are like light climbing out of a gravitational well. It costs energy. It requires constant effort, but it's possible. You are proof that it's possible. Now let me tell you something that changed how I see the world. Information is physical. This isn't a metaphor. Information has physical consequences. When you learn something new, when you understand a concept, when you remember an experience, physical changes occur in your brain. Neurons form new connections. molecules move, energy is expended, and that information, once created, influences the future. Your knowledge of gravity affects how you think about the world. The fact that you now understand that space-time can be curved, that event horizons exist, that the universe is expanding, this information changes what you'll think tomorrow, what you'll say to others, what questions you'll ask. You are a physical system that processes information. And information, like light, can propagate through space-time, influencing distant events. When I tell you that black holes can trap light, that information enters your brain. Neurons fire, patterns form. And now that information is part of you, physically encoded in the structure of your nervous system. And it can't be destroyed, not easily. Anyway, it's there. It influences your future thoughts and actions. So in a very real sense, by learning about light and gravity, you've been affected by gravity. Not directly. Earth's gravity isn't strong enough to trap light, but informationally. The concept of gravity shaping space-time has shaped the information structure of your mind. Here's what this means practically. You cannot escape being part of the physical universe. You are matter and energy, following the laws of physics, embedded in space-time. But you are also information, patterns of organization that can persist, propagate, and influence the future. Light escaping gravity is a metaphor for your own potential to transcend limitations. Not by breaking physical law that's impossible, but by finding pathways through possibility space that weren't obvious, by creating new configurations of matter and energy and information that didn't exist before. Every time you learn something new, you've escaped ignorance. Every time you solve a problem, you've escaped confusion. Every time you connect with another person, you've escaped isolation. These aren't trivial escapes. They're the ways that complex, self-aware systems navigate through the space of possibilities that physics allows. And here's the beautiful thing. Just as light can't escape from some regions of space-time, but can escape from others, depending on the geometry, you face different limitations depending on your circumstances. Some challenges are like being outside the photon sphere, difficult, but possible with enough energy and the right direction. Some challenges are like being inside an event horizon, genuinely impossible given the laws of physics and the constraints you face. The wisdom is knowing the difference, knowing when to push harder, when to find alternative paths, and when to accept that some things are beyond the horizon of possibility. But even when something is impossible, even when you can't escape a particular constraint, you can still do what light cannot. You can understand. You can find meaning. You can create value within the constraints. A photon inside a black hole has no experience of being trapped. It just follows its geodesic, oblivious to its fate. But you, facing your own limitations, can understand them, can work within them, can find purpose despite them. This is what separates conscious beings from mere matter. Not the ability to escape physical law, but the ability to understand it, to reflect on it, to find meaning within it. So when I ask you now, can light escape gravity's grip? I'm really asking, what does it mean for anything to escape? What does it mean for you to transcend limitations while still being bound by physical law? And the answer is that escape isn't about leaving physics behind. It's about understanding physics deeply enough that you can navigate its possibilities with wisdom. You can't escape space-time, but you can travel through it with awareness. You can't escape causation, but you can participate in it consciously. You can't escape death, but you can create meaning in the time you have. Light shows us this. Light doesn't choose its path, doesn't struggle against gravity, doesn't fear being trapped. Light simply follows the geometry of space-time, and in doing so, it illuminates the universe, carries information across cosmic distances, and makes consciousness possible by allowing eyes to see and minds to know. You are matter that has become aware of itself. Atoms forged in stars, arranged in patterns complex enough to reflect on their own existence, to ask questions about their place in the cosmos. The fact that you've spent hours exploring this question, can light escape gravity, is proof that you can escape ignorance, that you can transcend your initial state of not knowing. That information can propagate through the physical medium of your brain and change who you are. That's the real escape. Not from physics, but through physics. Not despite the laws of nature, but because of them. You are the universe understanding itself. Light trapped in black holes helped teach us about the geometry of spacetime. And now you know that geometry. The information escaped through Hawking radiation, through our observations, through the work of thousands of scientists over a century, and it reached you. So yes, light can escape gravity's grip. Not always, not everywhere, but often enough. Through direct paths when geometry allows. Through quantum processes when classical paths are closed. Through information encoded in correlations when direct escape is impossible. And you, made of star matter, illuminated by light, processing information, finding meaning, you are the proof that escape is not only possible, but actual. You exist. Therefore, escape happened. The atoms that make you escaped from stellar cores. The information that shapes you escaped from the minds of teachers and writers and thinkers who came before. The meaning you create escapes the moment and propagates into the future. You are both the light and the journey and the destination. You are matter escaping entropy temporarily. You are information escaping oblivion by propagating. You are consciousness escaping ignorance through understanding. And now, after this journey through curved space-time and quantum foam and cosmic horizons, you understand something profound about the nature of reality. That knowledge is in you now. It can't be taken away. It will influence how you see stars, how you think about time, how you understand your place in the cosmos. That's what it means for light to escape gravity's grip. Not just that photons can climb out of gravitational wells, but that information, understanding, meaning these can transcend barriers, can propagate across time and space, can survive even when the physical substrate changes. You are the current endpoint of a chain of understanding that stretches back through Einstein, Newton, Galileo, countless astronomers and physicists and thinkers who looked up at the night sky and asked, what is light? What is gravity? How does reality work? Their understanding escaped the boundaries of their individual minds. It was encoded in papers, books, lectures, conversations. It propagated through space and time, and it reached you. And now you can look at a star and really know that the light you're seeing escaped from a nuclear inferno, climbed out of a gravitational well, traversed the expanding universe, and arrived at your eye to complete a journey that might have taken thousands of years. That's magic. That's miracle. That's the universe showing you that yes, escape is possible. Light can transcend gravity. Matter can transcend stars. Information can transcend time. Meaning can transcend entropy. You are the proof. So after this entire journey, after exploring black holes and quantum foam, event horizons and cosmic expansion, gravitational waves and wormholes, determinism and free will, what's the actual answer? Can light escape gravity's grip? Here's the truth. It's not a yes or no question. It's a question about geometry, context, and what you mean by escape. Light outside an event horizon? Yes, it can escape. It might be red-shifted, it might be bent, it might take the scenic route, but it can get out. Light exactly at the photon sphere? It neither escapes nor falls in. It's trapped in an unstable orbit, balanced on the knife edge between freedom and capture. Light inside an event horizon? No, not because something is stopping it, but because out is no longer a direction that exists. The geometry of spacetime has closed off that possibility. Light in our expanding universe? It depends on distance. Locally, yes. Beyond the cosmic horizon, no. The expansion of space itself creates an impassable barrier. Light in quantum terms? Even inside a black hole, Information encoded in quantum correlations can eventually escape through Hawking radiation, though so scrambled that recovering the original information might be practically impossible. So the answer is, sometimes yes, sometimes no. Always it depends on the geometry of spacetime and the configuration of mass energy. But here's what's more important than the specific answer. The question itself has led us on a journey through the deepest mysteries of physics. By asking whether light can escape gravity, we've been forced to confront what light is, what gravity is, what spacetime is, what information is, what existence is. We've learned that gravity isn't a force, but the curvature of spacetime. That light isn't a thing but a wave in a field. That black holes aren't empty but seething with quantum information. That the universe isn't static but expanding. That reality isn't classical but quantum. That understanding isn't passive but active, creative, participatory. Every answer we found led to deeper questions. Can information escape black holes? Is spacetime continuous or quantized? Does dark energy get stronger over time? Is there quantum foam at the Planck scale? Are there wormholes? Is the holographic principle true? We don't know. We really don't know. And that's beautiful. That's exciting. That means there's still work to do, discoveries to make, understanding to gain. Right now, as you read this, there are physicists working on experiments to detect gravitational waves from the cosmic microwave background ripples from the moment of inflation that would tell us about the birth of the universe itself. There are engineers designing the next generation of telescopes that will image black holes in stunning detail. There are theorists writing equations that might finally unify quantum mechanics and gravity. There are students learning physics who will make discoveries we can't even imagine yet. The question of light escaping gravity is still being answered. The story isn't over. We're living in the middle of it. And here's what I want you to take away from this. Science isn't a collection of facts. Science is an ongoing conversation with reality. We ask questions, nature answers, and the answers lead to better questions. Can light escape gravity's grip? We've learned so much by asking. We've discovered black holes, gravitational waves, the expansion of the universe, quantum field theory, general relativity, dark energy. We've learned that the universe is stranger and more beautiful than we imagined. But we're not done. There are still mysteries. The nature of dark energy, the unification of quantum mechanics and gravity, the information paradox, the origin of the Big Bang, the ultimate fate of the cosmos. Every generation thinks it's close to understanding everything. Newton's generation thought they had it figured out. Einstein's generation thought quantum mechanics and relativity would soon be unified. We think we're close to a theory of everything. We're probably wrong. There are probably discoveries ahead that will overturn our current understanding as completely as Einstein overturned Newton. There are probably phenomena we haven't detected yet because we're asking the wrong questions. But that's okay. That's more than okay. That's the beauty of it. The universe is bigger than our theories. Reality is deeper than our equations. And the questions we ask evolve as our understanding grows. So can light escape gravity's grip? The answer is, light and gravity are both more subtle than the question assumes. Light isn't trying to escape. Gravity isn't gripping. They're both aspects of spacetime geometry, dancing together in ways we're still learning to understand. And you, by following this question to its depths, have participated in that understanding. You've traveled from basic concepts to the frontiers of human knowledge. You've grappled with ideas that challenged your intuitions about space, time, causality, and existence. That's what it means to be human in a scientific age. Not to know all the answers, but to appreciate the questions. Not to have reality figured out, but to be in relationship with the mystery. When you look up at the stars tonight, you'll see them differently. You'll know that the light reaching your eyes escaped from nuclear furnaces, that it climbed out of gravitational wells, that it traversed curved spacetime, that it's been traveling for years or centuries to reach you. You'll know that some light from beyond the cosmic horizon will never reach us. That information is being lost as the universe expands, that we're living in a special epoch when cosmology is possible. You'll know that at the center of our galaxy, there's a black hole from which light cannot escape. That spacetime itself can be so curved that directions cease to make sense. You'll know that gravity isn't pulling things together, but curving space. That time passes differently in different gravitational fields. That the universe itself is expanding, accelerating, driven by dark energy we don't understand. All of this will be in your mind as you gaze at the stars, and that understanding, that sense of wonder, that appreciation for mystery, that's what makes the journey worth taking. Because ultimately, the question, can light escape gravity's grip, is really asking, can we escape ignorance? Can we transcend our limitations through understanding? Can we find meaning in a universe governed by impersonal laws? And the answer that we've discovered together is yes. Not by breaking the laws, but by understanding them. Not by escaping physics, but by marveling at it. Not by leaving reality behind, but by engaging with it more deeply. You are matter that has arranged itself to ask questions about matter. You are the universe studying itself. You are light that has become aware of its own journey. And that capacity for wonder, for understanding, for finding meaning in the mechanical universe, that's the real escape. That's transcendence within physics. That's what it means to be conscious in a cosmos of curved spacetime and quantum fields and expanding space. Light escapes gravity when geometry allows. Understanding escapes ignorance when curiosity persists. Meaning escapes meaninglessness when consciousness reflects. You've spent hours exploring a single question about light and gravity. But in doing so, you've practiced the most human of all activities, seeking to understand reality beyond your immediate experience, asking questions about the nature of existence, finding beauty in mathematical truth. That's what separates us from mere matter. Not that we escape physical law, we don't and can't, but that we understand it, we marvel at it, we find it beautiful. So the next time someone asks you, can light escape gravity's grip? You can smile, because you know that it's not a simple question. You know that it depends on geometry and context. You know that it leads to black holes and quantum mechanics and cosmology and philosophy. You know that the answer reveals as much about the nature of reality as any question we can ask. And you know that by asking it, by following it deep enough, you've done something that light itself cannot do. You've understood. You've escaped ignorance. You've found meaning. That's the real answer. That's the real escape. And that's the real miracle of consciousness in a physical universe. Thank you for taking this journey with me. Thank you for caring enough about reality to spend hours exploring a question that most people never think about. Thank you for being the kind of person who asks, why and how, and what does it mean? Keep asking, keep wondering, keep seeking understanding,